Welcome everyone. Today we'll be discussing quantum Fourier transform. We'll be first remind about the discrete Fourier transform in signal analysis, and then we will go full quantum. And we'll discuss the way to implement this quantum Fourier transform via a circuit model. So the Fourier transformation is a very common tool in signal analysis. And essentially what it does is decompose a signal into its harmonics, as one can see from this equation. The inverse Fourier transform essentially is a very similar transformation. The only difference is that the phase factor is flipped by a minus sign. Now, this was the continuous version of the Fourier transform. For discrete signal, one can use the discrete Fourier transform. What the discrete Fourier transform, or in short DFT, does is that it takes an input sequence of D numbers that you can imagine be collected into a string of this form and outputs another sequence of D numbers. So it takes an input X and outputs an output Y. The rule between the transformation between X and Y is given by the fact that each of these number will be then given by a phase, by the sum over all the input numbers times a phase. Now, this is the direct discrete Fourier transform. We also have the inverse Fourier transform, and it's exactly the same except for a minus sign. The discrete Fourier transform is a linear map that maps a vector y into a vector x through a matrix capital omega. The element of the matrix capital omega are given by this formula. Essentially, they are just phase factor renormalized by the dimension of the space. Of course, there's also an inverse of this linear map, which, as we just shown, is just given by essentially the same formula except for a minus sign. Now, very importantly, the inverse transform is actually given by the Hermitian conjugate of this matrix omega. What this means is that this is a unitary operation, and as such, it's a valid quantum operation. This allows us to define a quantum Fourier transform, or in short, QFT. To define the quantum Fourier transform, let's consider an Hilbert space that has dimension d, which is spanned by a certain basic vector that we now call J. Now, the quantum Fourier transform is nothing else but a change of basis that maps this J unit vector into the quantum Fourier transform of this J, which essentially is the sum of all the unit vectors with a certain phase factor. There is a deep relation between the quantum Fourier transform and the discrete Fourier transform. To see this, let us consider an arbitrary input state phi, which is given by just some superposition of the basis state j with some coefficient x of j. Now, the Fourier transform of this vector, of this state vector psi, is just given by another vector in the same vector space, but with the basis function that are now transformed. And in particular, the new coefficients are related to the old coefficient by the DFT. So essentially, the quantum Fourier transform of a vector is just a new state vector whose coefficient are the discrete Fourier transform of the old coefficients. Let us now apply the quantum Fourier transform to the specific example of an n-qubit system. Now, the Hilbert space of this n-qubit system will have dimension d equal to 2 to the power capital N. And it will be spanned by a basis vector that is essentially a string of binary numbers, or can be described by decimal number as we did before. Another very important definition before we get into the quantum Fourier transform is the binary decimal. Essentially, what we do is that we take the decimal number and then we divide it by 2 to the power n. And then we will use this notation a lot, where essentially we just have 0 point the string. And by this we mean that we have different values of j, of the individual value of the string, will be then divided by the 1 over the appropriate power of 2. So this is a very useful definition because it enables us to also give a separate way of defining the quantum Fourier transform, which instead of being just a basic transformation given here, is given by just a tensor product of all qubits being in a superposition between 0 and 1 with an appropriate phase factor that is defined by the binary decimal. Now let's get into it. The quantum circuit that performs a quantum Fourier transform is given here. And essentially, it requires Hadamard gates that we already have explored quite a lot in the first module, but also control rotations. Now, these rotations, R of k, are essentially just diagonal matrices where the first entry is 1 and the second entry is just a phase shift that depends on how many times this rotation is applied. And it depends, that is labeled by this index k. These are control rotation, meaning that the rotation is only applied if the control qubit is in the state 1. Now let's see more precisely what this quantum circuit does. In the first step, we Hadamard the first qubit, meaning that the first qubit becomes in the superposition of 0 and 1. Now here, this is an alternative way of writing the state plus or minus. That accounts for the fact that when the input qubit J0 is in the state 0, we will get a plus sign here, so we will get a plus state. And when the qubit is in the state 1, we will get a minus sign, so we will have the minus state. The second step is to apply a control phase shift to the first qubit as a target qubit with control on the qubit J1. Now, what this does is essentially applying an extra conditional shift only if the control qubit is 1. We will phase shift the target qubit. So this means that we add in this decimal number an extra factor of J1. We can repeat this n times. And what we obtain is for the first qubit a state that is given by the coherent superposition between 0 and 1 with a phase shift that depends on the state of all the other qubits. So we do essentially now the same to the second qubit, to the qubit in state J1. And what we do find is a very similar state. But the only difference is that now the state of the qubit 2 will depend on all the state but the first qubit. So essentially in this binary number, we don't have the state J0. We now have to do for every qubit the same procedure, every time just reducing the number of rotation by 1. And what we do find at the end is exactly what we defined as the quantum Fourier transform earlier. We essentially find the tensor product of all the states being a superposition between 0 and 1 with an appropriate phase factor. Of course, this is just a direct Fourier transform, so let's see what happens with the inverse Fourier transform. And this actually is very simple because what we know is that the quantum Fourier transform is a unitary operation. So what we have to do is just to invert the direction of the application. So now we essentially use the same quantum circuit, but we apply the input state from the previous output. And then what we also need to do is Hermitian conjugate all the rotation. So essentially changing the sign in the phase of the rotation. Next lecture, we will see how to use this for quantum phase estimation.